Okay, so we're going to go back there and hopefully finish the last little bit of chapter 11. So last time we sort of finished talking about isomers, more specifically cis and trans isomers that do arise in alkenes because of the double bond. And a reminder that cis is the same side of the double bond, and basically trans is opposite sides. Now, as we talked about sort of last time, if you need to draw one of these, sometimes it's best to sort of draw it straight and then sort of readjust your drawing there. Cis 2,3-dichloral. So for example, cis 2,3-dichloral. 2-butene will work. 2-butene. So if we were to draw this, and regardless if we were actually to draw the cis or the trans, for example, regardless if the cis or trans, we would probably just want to draw it straight without any sort of geometry sort of located in it. So our butene would tell us that it obviously has 4 carbons. The 2 again means that the double bond is located at carbon number 2. So since you're drawing, you can put it either end. I'm going to go left to right, which means this right here would be carbon number 2, if I call that carbon 1. Dichloral means there's 2 Cl groups, one at carbon number 2 and one at carbon number 3, which would be there for me. And obviously everything else here would be hydrogens. I'm actually going to draw the hydrogens on this guy here. I'll get rid of my numbering there so it don't look so crowded. And so if I drew this straight, for example, and then I wanted to either draw the cis or really even the trans of this guy, what I would want to do is really just focus in on the carbon-carbon double bond. And I would start with that. And at this point, I could also sort of identify, and again, here I have, sorry, I have too many hydrogens there. There should not be hydrogens there. I'm sorry. Don't draw those hydrogens in. That's better. I would want to identify my groups. So obviously I have a Cl and a CH3, a CH3 and a Cl. And again, if I wanted to draw the cis, I could just simply put either actually the methyl groups here or the Cl groups on the same side. And I could really sort of draw it showing the cis or trans by just translating it like this. If I wanted to do this would obviously be cis. If I wanted to do the trans, I could start with the same thing, just start with my carbon-carbon double bond. And then if I wanted to do trans, obviously I would do 1 chlorine up and 1 down, and 1 CH3 up and 1 CH3 down, and that obviously would get me trans. So sometimes if you're asked to sort of draw these guys, it's sometimes easier to maybe make an extra picture, just kind of the straight picture, isolate the double bond, and then kind of move the groups to where you need. Don't add an extra hydrogen like I did there. That shouldn't be there. That's also a good idea. The other important thing when you do have these sort of structures drawn with the cis or trans showing, as we I think finished up with last time, is the idea that you do want to make sure if you are asked to name it, that you don't just focus in on the double bond. It's very common people go, okay, longest carbon chain is 2 because it's sort of drawn that way. So as we talked about, really in this case, longest carbon chain is like 1, 2, 3, and obviously 4 going that way. And in this case, going this way, right, would be that. So make sure, sometimes people get really focused in on the double bond, especially when they're drawn like this, and they kind of mess up the name and stuff like that, thinking that, the other parts are just groups and stuff like that. Obviously as well, if you did some type of line structure where you wanted to kind of show that, you would still start really with the double bond. You just draw it like that. Obviously there's a carbon obviously on each end of those lines. And then if you needed to do, say, the cis, you could draw down to a chlorine and a chlorine, and then up as actually there would just be methyl groups, so there would be nothing at the end of those lines. So you would just draw a line up and a line up, with those would obviously be the methyls and our chlorines there. Or if you wanted to do trans, you could do a chlorine and a chlorine and a methyl basically. Here it would look something like that. Any questions on that there? Okay, so what we want to finish up talking about here is some reactions that these alkenes undergo, and they basically undergo a type of reaction which is known as an addition reaction. And it's much like the name implies, we're actually going to add things in. So kind of similar to what we were doing earlier, and not take anything out, which is sort of a substitution reaction. And pretty much, as I mentioned before, everything always happens in one location. And when you're doing these reactions, it is always the carbon-carbon double bond is pretty much where it happens. Doesn't matter what else is attached on either side, it is always going to happen here. And basically, if you add something to it, basically what we're always going to do is that double bond will become a single bond to make room for it. And you basically just add one thing to each of the carbons. And that's always sort of what happens. They do go to opposite carbons, and double bond always becomes a single bond. So that is always the general thing that happens. Double bond becomes single bond. And you basically just add in those things, one to each of the carbons. Again, absolutely nothing else changes outside of making that into a single bond. There's nothing that leaves and makes on the side. It's all just added in. The reason we got some margin here is this process, for example, when you add hydrogen, as we will see, is what's known as a hydrogenation reaction. Perhaps you've heard of things being partially hydrogenated. That's basically what it means. When you take out some of the double bonds, especially when you have fatty acids, as we'll talk about, fatty acids have long carbon chains. And if you have no double bonds, all those carbon chains fit really nicely with each other when you have a bunch of them, and it makes things like fats more solid. When you have double bonds in there, the double bonds don't allow these things to sit nicely with each other. They get kinked in the chain, and they're more like oils at sort of room temperature. So you could take an oil and add some hydrogen to it, get rid of some of the double bonds, and then you get margarine that you could put on your bread and all that good stuff along the way. So addition reactions are really broken up into sort of two types of reactions. They are sometimes what we refer to as symmetrical additions, which basically means you're adding two things that are the same. So the hydrogenation reaction is when we add H2. So you're just adding two hydrogens. You know, you could add, for example, two bromines or two chlorines. But symmetrical basically means, and they are kind of the easiest of the two in a sense, because basically all you have to do is break the bond into a single bond, and it's the same thing goes to each carbon. So you can't really mess it up in that sense. And there's also unsymmetrical additions. And unsymmetrical additions are when we add basically hydrogen and something else. So very common ones, adding hydrogen and OH, which is water. Again, this is basically water. Add something like HCl, HBr, basically hydrogen and something else being added in there. Now, in the first case, you know, you get a very simple sort of reaction. In the second case, there is sometimes rules that you have to follow depending on where the hydrogen ends up. So let's take a look at each of these here a little closer. Sometimes they do need catalysts. Catalysts are sometimes written on top of the arrow. catalysts are not reactants. They're not products. They don't get used up in the reaction. So I think we talked a little bit about catalysts in an earlier chapter, but they're there basically just to speed up the chemical reaction. So in the case of organic chemistry, they really aren't incorporated into anything that you would draw. On the product side, they're just there to kind of facilitate the reaction occurring faster. If you ever see H plus on top of an arrow, that means it's an acid being used as a catalyst as well. So let's first take a look at these symmetrical additions where we're adding the exact same thing. So we'll look at something like, we'll take this guy here. And we'll lay a double bond there. Why not? Let's put a chlorine there as well, just to make it fancy. There we go. It's fancy chemistry today. There we go. All right, so we got an alkene here, and we're going to add something like H2 to it. When we add H2, it's basically 2 hydrogens. So once again here, as I mentioned, although there's a bunch of stuff sort of drawn on there, really the only place of focus that we should have is right there at the double bond sort of location. And what I'm going to do is know that this is going to be an addition reaction because I'm starting with an alkene. And that means that pretty much I can once again redraw exactly what I have there, except that I do need to make room for those guys to come in. So I'm just going to break the double bond and make it a single bond. So I'm just going to draw it underneath. So I ran out a little bit of room there. So CH3, CH, we have our Cl. I'm just going to draw the hydrogens that were there originally. I'm going to make the double bond into a single bond. Again, I'm just going to draw this hydrogen out so we can see it. You don't necessarily have to, but I'll just draw it out. And at this point, what we've now done, and hopefully you can see it a little bit easier with the hydrogens drawn, is this carbon now can accept something, right? Because it only has 3 bonds. And this carbon now, by getting rid of that double bond, could accept something. And what they're going to accept is basically a hydrogen each. So they're both going to get each a hydrogen. So we would put each of those hydrogens on. One there and one there, right? So those would be our hydrogens there that we would put on. And we basically go from an alkene to an alkane here. This is what is known as a hydrogenation reaction because you are adding hydrogen. That's a fancy way of saying I just added hydrogen basically to that. Pretty much every single alkene reaction that you add 2 of the same work exactly the same, no matter if it's a ring structure, if it is a guy that has a bunch of carbons, a bunch of stuff attached. The only thing that changes is you turn that double bond into a single bond and you add each of the things over there to the other side. Question on that there. So why don't you try a couple here and see. So why don't we do let's do let's do to mix it up. We'll do this Br2 here, and this guy should have a hydrogen as well. And then why don't you do this guy plus H2. All right, let's take a moment or two, draw the products here of each of these. Okay, let's take a look. So once again, even though it looks really big and all that good stuff, and there's, things attached all over the place, the one thing you want to look at when you look at this is I see something with a double bond, so that's an alkene. I'm adding something to it, so it's probably going to be an addition reaction. Once again, once you know that, you should know it always happens in this order. We just make the double bond into a single bond. Everything stays the same. So again, we just want to focus in on, first off, getting a lot of our picture down on the paper by just simply copying what's there and turning the double bond into a single bond. So that would be really the first thing that I would do is, frankly, like I said before, just kind of copy what's there. And once again, understanding that it is just that double bond location as to where anything changes. And that is really the major change you're going to do at this point, which is just to make it a single bond. And I'm just going to copy everything else exactly the same. Again, nothing's really moved. In this case, we're adding Br2, which is 2 bromines. The point of turning that into a single bond is now we have room on each of those carbons to accept a bromine, and each will accept one on each one. And frankly, since it is the same here, you again, doesn't matter which one you put where because they're both bromines. Any questions on that one there? So again, like I said before, sometimes people get a little mixed up and start thinking, well, it's got to be a lot more complicated than it should be, and it's not. So again, don't do anything weird like break it apart into 40 different things or anything crazy like that. When we look at the bottom one, that's a ring structure there that has a double bond. So once again, we do see a double bond plus something being added to it. So our focus should again just be drawn to the double bond part. And again, we're just going to make it a single bond. We're not going to open it up or make it straight chain or anything like that. We're just frankly going to draw our triangle without the double bond, but still obviously keep the guy on the other side as well. What that technically did is open up these carbons here to accept, in this case, a hydrogen each. And in reality, since this is sort of a ring structure here, you don't actually need to draw the hydrogens in there, but I'll draw them in just to show you. This guy technically just gained a hydrogen from the left, and he gained one there as well. When it originally started, because there was a double bond there, it only had one hydrogen. So again, we added an extra hydrogen there because now it's a single bond and it technically has 2 hydrogens at each of those locations, but 2 were added at this point. Any questions on those symmetrical additions? So let's talk a little bit about the unsymmetrical. Yeah. Yeah. Hi, how you doing? Good to see you again. Are we talking about this one? Yeah, okay. I actually didn't add 4 hydrogens. It started with 2 to begin with. I just drew them up. These would be these 2. The ones in red that kind of match these red here were the ones that were added. Yep, yeah. Yeah, so it's kind of the same thing as the one we just did here on the bottom. Technically speaking, before we did anything, they actually had a hydrogen each. So we added basically 2 hydrogens. And really, because it's sort of line structure, these guys are usually drawn. You actually, most of the time, would just draw it like that, which would imply there's, again, still the 2 hydrogens there, one of which you added to each of the carbons and stuff like that. But for illustration purposes, you could draw the hydrogens out if you wanted to. But in this case as well, they each started with 1, and then they gained 1 from the addition of those hydrogens. Yeah, you're welcome. Other questions? Then let's talk about those unsymmetrical additions. And this is really a situation where, frankly, you add hydrogen and something else, basically. So if it's water, you're adding hydrogen and OH. Like I said before, if it's like HCl, those are the two things you're adding, H and Cl. If it's like HBr, it's H and something else. So these are unsymmetrical basically because you're adding two different things. So in the previous examples, what we were adding in were both the same. So frankly, it didn't matter where you put it because it's all going to end up the same. So in certain cases, it does matter in this situation where you put the hydrogen. We'll talk about both of those situations in just a second, but let's first take a look at one here. So let us again sort of draw up a double bond situation here. We'll do this, and I'll draw out the hydrogens that were here to begin with. And in this case, let's say we did add water, which is H2O. And again, when we're adding water for this purposes here, you could think of it once again as H and OH. So what's being added to one carbon will be the hydrogen, and what is being added to the other carbon will also be an OH group. Now, in this particular case, what's going to happen is the exact same thing that happened in the previous example, which means, again, I see a double bond and I'm adding something to it. So my focus, once again, should go directly to the double bond. And it's going to change exactly the same way, which means we are going to make it into a single bond. So really, it has room to accept each of those things that are coming in. So once again, you could draw this pretty quickly by just frankly copying what is there, making the one small adjustment, which is double bond is now a single bond in this particular case. And as I mentioned before, the purpose of this is really just to make room for what's coming in. So what's coming in is a hydrogen is going to go to one carbon and an OH is going to go to another. So we can put that on. And I'll just draw it in red. So I'm going to add a hydrogen here and an OH here, right? And this gives me what type of compound? This is a alcohol. Yeah. So this is really how we prepare an alcohol is you take water and you add it to an alkene. So you go from an alkene to an alcohol through adding water. This type of reaction is what is sometimes referred to as a hydration reaction. Hydration because we added water. So earlier today, I think maybe the other day as well, we did a dehydration reaction, right? Where we took the water off. This is basically putting the water on and making an alcohol. And that's why what we saw earlier today, and I think the last time as well, when you took the water off, you ended up with the alkene. So if you start with an alkene, put water, you get an alcohol, take the water out, you go back to your alkene in that particular case. By the way, this is what type of alcohol here? Primary, secondary, tertiary. It is a secondary, I think I heard, yes. And it is because this carbon is attached to one and two other carbons. So this would be a secondary alcohol in this particular case. Now you may ask, because it's two different things, does it matter where you put it? And in this particular example, it doesn't. So let's name this guy first off. What would the proper name of this guy be? I like the butanol. Do we feel like there should be something else with it? Like a number? 2-butanol, sounds good. I like it. So this is 1, 2, 3, 4, right? Which would be butanol. And then obviously given the OH, the smaller number would be numbering right to left in this case, right? That'd be 1, 2, and that would give you 2-butanol. So let's just say, for example, we added it in the opposite order. So we put the OH on the left and the H on the right. So what I'm going to do is just redraw it and do what I just said is basically just add my guys in the opposite way, which is clearly an option in this case because you're adding two different things. So now instead of adding the H there to the, let's come back somewhere, come back, there it is. So instead of adding the H to the left there, I will add my OH and I will add my H. So basically just kind of did the opposite of adding there, right? Which would be your other option. By the way, this is still a secondary alcohol. And if I were to name this guy properly, what would the name be? It is still butanol. And do we have a number for this guy? Well, we want to give the OH group what type of numbering? Smallest. So we would need to go in this case left to right, which would be 2-butanol. It's actually the same thing in this case, right? So this is what I'm explaining in this particular example. There is really no difference where you add the H or the OH. And the reason for that is the actual number of hydrogens that are attached in the double bond to start with. Each of the carbons that are in the double bond have how many hydrogens? Each of this carbon has just one hydrogen each, right? So they're basically equal in a sense. So in the case where that happens, it really doesn't matter where you put the H or where you put the OH, or if it was like HBr, it doesn't matter. Now, if we were in a different situation where they actually did not have the same number of hydrogens, it would actually make a difference. So let me draw one like that and we can kind of see the difference here. So let's take, let's do our same 4 here. And we will double bond there, but I'm gonna put a CH3 there, I think. Okay, so we'll do that, we'll do that, we'll do that. All right, so I'm gonna take this guy here and I'm gonna add, and again, it doesn't matter if it's water or anything else, or HBr, HCl. We'll do water one more time here. So we'll add our water, which is HOH, right? So once again, even though it kind of looks different, what we're going to do is focus once again on our double bond, and we're going to turn that into a single bond. And we're going to redraw it exactly the same way. And as we did before, we're going to turn the double bond into a single bond. We're going to keep everybody else exactly the way they are at. And now we want to add our H and OH, right? So we have room to do that. So in this case, you have 2 options. I'm just going to redraw it on the bottom one more time to show the 2 different options as to where we could add it. Okay. Option number 1 would be to put our H on the left-hand carbon and our OH on the right-hand carbon, right? And option B would be basically the opposite there, to put our OH on the left. If I could find something to draw that with. And our H over here on the right-hand side. Now, first off, what did we make? We still made a alcohol in this case, right? By adding water. So again, this would be a hydration reaction. What see, are these 2 things the same or different? And we could find that out by naming them. So once again, the name of this guy here on the top, what would number 1 be named? It is butanol again. And the number that would go with that for the OH group should be 2, because going this way, right? We'll give that guy the smaller number. Because we went that way, there is also a methyl group at carbon number 3. So this would be 3-methyl 2-butanol, right? Now, the bottom guy, number 2 there, its name would be butanol again. The number for that guy would be, it would still be 2, because we want to go this way. 1, 2, 3, 4. Now our methyl group is on which carbon in this case? It's actually on carbon number 2, because of the way we had a number for the OH group. So this would be 2-methyl 2-butanol. Are they the same thing? They are not, right? They have different names. So in this case, there is actually a difference. depending on how you add basically the H and the OH, right? You get two different things. The result of that is it goes back to the carbons in the original guy, double bond. The carbon on the right has how many hydrogens? Has one. Carbon on the left has none in this case, right? So because they have different hydrogens in that double bond, when you add something that is unsymmetrical, two different things in, you actually could get two different products. One is sometimes referred to as the major product, and one is referred to as the minor product. And in most cases, you want to usually shoot for the major product. And there actually is a rule named Markovnikov's rule. You can reference your book for the proper name of that, but it's Markovnikov's rule. Don't ask me to spell it because I will spell it wrong. But basically his rule was that when you have a situation like this and you have a double bond and you're adding two things that are different, like water, HOH or HCl or HBr, it is the hydrogen should end up, and the hydrogen we're adding, we're talking about here, on the carbon that started with the most hydrogens. So when we add hydrogen to something else, we want to actually put the hydrogen on the carbon that actually began with the most hydrogens, which means in this case, where should the hydrogen actually end up? Should end up on the carbon on the right? And that means that actually the major product is actually the bottom one would be the major product in this case, as we put the hydrogen on the carbon that had the most to begin with. So in a case where there is a difference, obviously in the previous example, both of the carbons had the same number of hydrogens, so there really didn't make a difference, as we saw with the name, right? No matter which way you put it, you get the same name. But when you do have a carbon with a double bond and each of those carbons have different numbers of hydrogens directly attached to it, is obviously what we're talking about here. The hydrogen that you're adding in should go to the one that has the most hydrogen to begin with. And that's sort of opposite of, if you remember in our dehydration reaction where we took the water off, we actually would take the hydrogen from the one with the least number of hydrogens if there was a difference. And that's where the double bond would go. So Markovnikov's rule is hydrogen being added in this situation should end up on the carbon that started with the most hydrogens directly attached to it. And then obviously the OH or the Br or whatever else is attached would go to the opposite carbon. And that will give you your major product. And that's typically what you should draw. Question on that there. Yeah. Yeah. Are you asking how many hydrogens this one has? So what we're looking for is actually the hydrogens that are directly attached to it. And in this case, it actually has 0 hydrogens, right? There's no hydrogen directly attached to this guy. There are hydrogens this carbon, and the hydrogens here are attached to that carbon. The hydrogens here are attached to this carbon. But there is no hydrogen directly attached to that guy, like there is to this carbon here. It has one that is directly attached. And that's what we're looking at when we're trying to decide that is in that double bond directly attached to the carbons in the double bond, which one has the most, if there is a difference. And that's why when we looked at, say, this previous one, when we looked at the double bond, we could see directly attached to that carbon is 1 hydrogen, and to this carbon directly attached is 1 hydrogen. And again, in that case, because they were both have 1, it doesn't make a difference. And it's only when you have different amounts of hydrogen in this situation, it would make a difference. Other questions on that? All right, why don't we try one here, I think. Let's take a look. Let's do. Wow, we had some HCl, a little bit, something different, I think. And what we do, All right, why don't you try both of those, see what you come up with. Yeah.
So when we're writing it out, so writing out the name, I get confused. Are we doing it in alphabetical order? Like, so this one has a plural and then the meth.
So if you were to name this guy, the first thing that we have here,
I know what's in there. I just don't know how to write it out because I'm not sure if I'm going off the number or the alphabetical order of them.
if you wanted to name the original guy that's up there, is that what you're asking? Yeah, so you would do the same thing. So in this case, the functional group is the double bond, right? So it's got to be part of the longest carbon chain, which would pretty much encompass all of that, right? And that would then be 1, 2, 3, 4, 5 carbons. And because it has a double bond, it would be pentene. And we would need to give the double bond a number, and we would want to give it the smallest number, which means we would probably want to go right to left, right? Yeah. And that would be, as you said, there are 2 pentene. Now we do have, as you said, a methyl group and a chloral group, and we would want to go alphabetical order. Even though the chloral group has a larger number, it would still go alphabetical if that's your question. So it would be something like 4 chloral, 3, I'll try to squeeze in there, methyl, not 12, but methyl 2 pentene would be the name there. So something like 4 chloral, 3 methyl, 2 pentene. And again, even though, number wise, this guy's bigger, you do go by alphabetical order, regardless of the number, if that's sort of your question. And also if you had like a prefix, like a dichloral or something like that, you would go by the chloral part rather than the di part. Yeah. So regardless of prefix. Good. Yeah. All right. Get here when we draw. I wanted to draw, if that's okay. All right, once again, we obviously have a double bond alkene going on there. So it is the double bond, which we automatically know just going to become a single bond. And in this case, we're just going to redraw it exactly the same. And again, obviously make our double bond into a single bond. Now in this case, we're adding the H and Cl in. Doesn't make a difference in this case where the H ends up. It does, because when we look at the double bond, guy on the right has 1 hydrogen, guy on the left has none, right? So the hydrogen should end up on the guy on the right, and the Cl should end up over here. That would give us our major product in this case. Yeah. Any questions on that one? Obviously, if you reversed it, you drew the minor product, which you probably don't want to shoot for, I suppose. Any questions on that one there? Now we have a ring structure over here where, once again, we're not going to be so concerned about it other than our double bond that's in there. And just like we did above, we're just going to simply redraw it and make it into a single bond. Now, if we do that, it looks exactly the same. It also still has our methyl group hanging off of there. Doesn't make a difference in this case where the hydrogen ends up. So let's take a look at the double bond in our original spot. This hydrogen right here, does it have any hydrogen? This carbon right there, does it have any hydrogens? It has how many? It actually has only 1, as there's 1 line here, right? 2 and 3 lines coming into it, which means it has just 1 hydrogen. How about the carbon here? How many lines is going into that carbon? There is actually 4 lines coming in. 1 here, 2, 3, and 4, which means that carbon has how many hydrogens? It actually has none, right? Because it's already got 4 lines coming in. So in this case, the hydrogen actually should end up on top, right? And down here is where the Br should actually end up in this case. And again, because the guy on the top there had more hydrogens to begin with. By the way, it actually has another hydrogen that was there originally. Just for reference sake, I'll circle the one that was added. I'll just circle them for the two things that were added in. Obviously, the hydrogen was there originally as well. Question on those there. Question on addition reactions. Okay, then let's take a look at the last little bit here. I'm just going to kind of go through these. These are sort of the reactions we obviously just talked about. So obviously this is a hydrogenation reaction where we turn our double bond into a single bond. And obviously this is symmetrical. So we're just adding the hydrogens in like we talked about there, one to each side. Once again, this stuff on top is just a catalyst, not really going to do anything to the product that you're drawing in that particular case. So if we were to draw the hydrogenation of one butene, butene is obviously 4 carbons. 1 means the double bond should be at carbon number 1. And this guy would have some hydrogens going that way and something like that. In this case, since we are adding hydrogen, which is H2, we really don't have to worry about it because it's symmetrical. So we're just adding basically the same thing to each side. We will do the exact same thing we did previously, which is basically just turn that into a single bond. And we would copy it exactly the same. And draw the right things there. That would be good too. And then obviously in this case, we are going to put where we have the double bond our hydrogens in there. And again, going from an alkene to an alkane, in this case, doing this, which is a hydrogenation reaction. Again, very similar to obviously what we talked about a second ago. Any questions on that one? Okay. So as I mentioned before, hydrogenation of oils will turn it into things like margarine. And as we'll talk about with our fatty acids chapter there, it's those double bonds that really sort of allow things not to sit really good with each other and become more like oils. Again, by adding hydrogens in there, it allows these guys to really sit really flush with each other. And it turns the fat more into a solid than a liquid at that point as well. So I'm going to draw these in case you want to look at them. But again, they're very similar to what we did before. So we can finish up the last little part that we need to talk about. What happens here is just going to add in the hydrogen here and a hydrogen here and CH3. Then obviously here, we're going to add a hydrogen where the double bond was. So I'll draw it, even though you don't technically need to draw it. It will look something like that. And again, it's basically the exact same stuff that we've talked about. So if you want to look back on the video, you could look at it there. So we can get to the other stuff there. And this is obviously our hydration reaction where we added our hydrogen and OH to it. It is done usually with the source of sulfuric acid. So sometimes in reactions, you'll see sulfuric acid written there. It's just really there as a catalyst to do the hydration reaction. So you don't have to incorporate the sulfuric acid into the product. So sometimes people will want to do that because sometimes it's even written like not on top of the arrow, but they'll maybe just sometimes put it like next to it and stuff like that. So if you do see that, it's probably has something to do with adding water like we did previously, and don't incorporate the sulfuric acid into the reaction. So once again, here we would add our water in, and once again, in this case, we would make our double bond into a single bond. And you're going to tell me, is there a difference where the hydrogen goes? So this where I made the single bond here towards the end has 1 hydrogen. This guy has 2, which means really the H should be added here up in a box. and the OH should be added here, right? Again, it has the most in that particular case. Any questions on that there? And again, this is they'll sometimes write sulfuric acid or just H+, and again, none of that gets really incorporated into the answer. All right, so last thing I want to talk about here is aromatic compounds, and aromatic compounds are our benzene compounds, and benzene is a 6-carbon ring that has 3 double bonds in it. It's sometimes drawn like that. It could do a resonance structure where the double bonds go to the other side. But a lot of times, even in your book, I think they just kind of lay up a circle in the middle of it as well. And that's really because the double bond electrons are delocalized, so they are free moving around the ring. So at any given point in time, the double bonds could kind of arrange like this, but then they could kind of move and sort of arrange themselves in that sort of way. So sometimes in this type of organic chemistry, they'll sometimes just draw the little circle in the middle to indicate that. Now, aromatic rings, as you can see here, oftentimes are kind of drawn like that. If you were to draw out the hydrogens, which is usually not done, because of the 3 double bonds, there is a hydrogen at each of those carbons to get carbon, obviously, to 4 bonds. Don't miss it there. That's a single bond there. Now, there are certain historical and common names that are used with benzene when they have certain groups attached. And these are a few that you should be familiar with. If you have a benzene ring that has an OH group, we saw this when we were talking about alcohols, that is what is known as phenol, and that sort of becomes the main part of the name. If you have a benzene ring with a methyl group attached, it is historically known as toluene, and that's sometimes still used. And if you have a benzene group with a NH2 group attached, that is known as aniline. So that is an amine group attached. If you wanted to do sort of the non-historical name, something like this would be known also as, that is a methyl group attached to benzene. So that would sometimes be referred to as methylbenzene. You know, if you had some type of chloral group on top of there, it would be chlorobenzene. And obviously, if you have just one group attached, you don't have to give the location of where the group is at. It's assumed to be carbon number 1. So you could just simply give the group name and put benzene at the end. But again, these sort of historical names are still used a lot still today. So if you see those historical names, they sort of refer to those guys. And if you have multiple groups attached, you still want to give everybody the smallest number. So if we had 2 chlorines attached, that would be what is referred to as 1,2-dichlorobenzene. And it don't matter which way you go here because there's double bonds all over the place. So you could go right to left and left to right. This guy is a carbon number 1, going here to carbon 2 to carbon 3, would give us 1,3-dichlorobenzene, and calling this carbon 1, 2, 3, and 4 would give us 1,4-dichlorobenzene. So obviously, if you have multiple groups attached, you do have to give a number. Now, when you have a benzene ring, these positionings are also sometimes referred to by other names. The 1,2 positioning on the ring, like this guy. The 1,2 position on a benzene ring is what is known as the ortho positioning, or just O. The 1,3 positioning that we see here is known as the meta positioning, or just M. And the 1,4 positioning on a benzene ring, and only a benzene ring we're talking about, is the para positioning, which is sometimes abbreviated with just a P. And sometimes those are used instead of the numbers. So for example, if we took this guy here, because it's the 1,3 positioning, it would sometimes be just meta dichlorobenzene, where they'll just use the they'll just use the M for meta, or may say meta instead of the numbering. This guy here would be para dichlorobenzene or P dichlorobenzene. So if you see like an O, an M, and a P with a benzene ring that has a couple groups attached, that is basically the positioning of where you would find those groups on position 1, 2, 1, 3, or 1, 4. Any questions on that there? So again here, if you look at these guys, we have our aniline, which is where that name comes from, with our group being 1, 2, and 3 for our bromo. This is our phenol group, along with our other groups attached. Again, going counterclockwise in this case gives the groups the smaller number for our 4-bromo 2-chlorophenol. And here, this is toluene here with actually 3 groups attached and numbering accordingly. And lastly here, this again would be a benzene ring with a chlorine on it, which would be just chlorobenzene since there's just 1 group attached. This would be a benzene ring with 2 methyl groups at position 1, 2, and 3, which would be 1,3-dimethyl benzene. Or since 1 and 3 is the meta, it would be meta-dimethyl benzene as an alternative name. Any questions on benzene or aromatics? All right, thank you for hanging in there. That should wrap up chapter 11.